Okay, so hello to my professor and to whoever ends up watching this on YouTube. This is going to be my final project demonstration of all the projects I've been working on in my design of manufacturing tooling class for Oregon Tech in Portland, Oregon. So let's just get to it. I had three projects. I had a bar stop part, a door roller shaft part, an injection mold part. Basically, for all of these parts, the idea was that we have a customer that wants to produce these and they need a turnkey solution. So that includes fixturing costs, cam design, fixture design, just basically everything that would be needed. So I'm going to try and give you guys a high level overview of each of my projects. So the first one is the the first one is the bar stop. That's this part right here. It's a tiny little part. It's about, what's that, 7/8 by quarter by about a half-inch tall, so it's a really small part. And I immediately saw that and thought that it should be done on a turning center, but the project wanted you to design some fixturing, so I decided to do a mill and a turning center and basically compare the two and see which one is more cost effective. And I created a spreadsheet, which I'll show you guys, which kind of details the different costs involved depending on the machine you're running it on. So on this mill, basically I have three vacuum chucks. These are Pearson work holding pallet centers, or vacuum pallets. Basically, these pallets sit on the bases, and you pull a vacuum and it sucks all these pallets down, and then when you release vacuum you can pull these off. And the advantage is that the operator does not have to spend time unclamping and reclamping all the parts. While the machine is down, the operator can pull these off, have two sets rotating at all times, so that the spindle has maximum uptime, which is important for shops. So I'll just go ahead and show you like the operations for the milling, and then I'll show you how I did the cam for the lathe. So here's the raw stock. It comes in. Also, I'm using these Mighty Bite expansion clamps. They're pretty cool. You screw this Allen down and then it squishes on both sides, so you have one screw for two parts. So that's your stock. This is the first operation on the mill, just roughing out that profile. Now we flip it over. We rough out the profile on the other side. We blend the tooling passes. Hopefully we do a good job blending those. It comes over here, gets kicked up on its side. This is the third op. Come in with a slitting saw, slit that out, get rid of this little fillet here, make it a square corner. We drill the holes and we tap the holes, and then you have a finished part. And it's a small part, so this is a VF2, a Haas VF2, Haas VF2 vertical CNC mill, and you're able to fit quite a few parts on these. So that's that, but now I want to show you the cam for the turning portion. We'll go ahead and simulate that. Alright, cool. And I apologize, the environment in Fusion is kind of clipping into the simulation, which is kind of bogus, but that's what it is. Alright, so we're going to come in here. We face off the front. We rough out the general profile of the part. Come in with a nice big, stiff half-inch end mill. And we cut out that little square pocket. Coming with a slitting saw. I realize it does one pass. It should do more than one pass with the slitting saws, but I'm not actually machining this part, so I didn't make all the tool paths perfect. Right there, we go ahead and plop 3 holes in it, and then we're going to come back with the tap and hit those 3 holes. Now we come back with that nice rigid half-inch end mill and just kind of get the outer square profile done. And you can see the end mill is just long enough. So there it goes, does that. And then I believe the next operation, it's doing a finishing pass right there. I believe the next operation is slitting saw, or not slitting saw, but parting off blade. So there it goes, parts it off. Bam, it's done. Much quicker than the mill and much less involved, because ideally you would have a lathe with a bar feeder. So this would all be automated. As long as your tool life management is dialed, it's pretty automated. But that's just the nitty-gritty details. Anyways, yeah, so that's the, I guess, cam portion of the project. Let me go over to the spreadsheet and show you that. Let's go find that. Let me just pull it up real quick. Bar stop cost comparison. Yep, here it is. Oh. Alright, here we go. Go to the top. Okay. So basically, you can see on the left side I did milling and turning. And I apologize for going fast, but I'm trying to squeeze all my projects into a 20-minute video. So on the left, you have to buy a ton of fixturing because mills don't have built-in fixturing, whereas the lathe, you already have a chuck, so there's literally no fixturing price. So right off the hop, $8,000 for milling, $0 for turning. Tooling list, about the same. Cutting calculations. So I pulled up a little graph to try and estimate tool life. I think this was going to be stainless steel, if I'm not wrong. But yeah, I found the life, found the time in the cut. I took basically the machining time and separated it out to milling and turning and tried to figure out. Basically, I took how long I thought it was going to last, and then I multiplied that out with the time in the cut and cost per tooling. So the cost, lathes generally, since they're peeling off material, they're taking less wear. They're a little nicer to the inserts, so you are spending a little less in tooling for the year. And then if we look at time, you can see over here, let's just look at it. Machining time is like about 4 minutes for turning, and over here it's about 4 minutes. Yeah, 1 40 40. That's 3 plus. Yeah, so they're actually they're pretty similar in the time it would take to cut it out. But the real advantage is that with this guy, if you run it, I estimated that it would run 60% of a standard week. So that's like one shift, one guy at the end of the shift loads all the bars and it runs into the night. So I estimated that the machine is running 60% of a standard 7-day work week, which goes out to about 1,500 parts a week. Whereas if we go to the left side with the mill, and we assume this machine is running 3 shifts, 5-day work week, because it can't run on the weekends, it's only 1,440 parts. So the conclusion is that you'd actually need 2 mills running 3 shifts on a standard 5-day work week, which is a ton of labor to pay. And then with the lathe side, you would need 1 lathe with a bar feeder and proper tool management, and only 1 shift is needed to run automatically. So you're saving 2 shifts. You're paying 1 person a day instead of 3 people in a day. And yeah, labor is expensive. So we really see that breakdown here in the labor cost. The cost of 2 workers for 3 shifts for a whole year is about $25,000. That's at $20 an hour. And then the cost of 1 worker for 1 shift for a whole year is about $42,000. So you can see that labor cost on the lathe is a ton cheaper. Material cost, you have to consider that on the turning or on the machining center on the mill, we have to buy it and then we have to cut it to size, which is, there's added cost in cutting it. And then on the right, it just ended up that the 303 stainless bar, round bar, was cheaper than the square bar. Same suppliers and all that. It just ended up being cheaper by about $50,000 over a year. So here's the summary. Here's the breakdown. At the end, so the first year we have some cost of tooling and stuff and setup. So it ends up being 65,000 parts a year, and 65,000 parts is going to end up at being $707,000 basically. And then after that, you drop all your tooling costs because you already bought it, or you drop all your fixturing costs because you already bought those. So it goes down to 680. Whereas over here, It's actually about half. First year cost $388. Reoccurring cost is $378. So it actually is about half the price if you compare to having a milling machine. And you kind of also have to look at process reliability. When you're touching that many parts on a mill, the operator might give inconsistent torque on the parts and all that. So you might have a higher scrap rate, or an operator might damage the fixturing. Whereas a lathe, it's kind of like set and forget. I mean, of course, things can always happen, but I just feel like on a lathe, there's less room for error. It's a little more scary, but there's just less room for error once everything is dialed. But that's pretty much this project. So before I kill too much time, let's move on to the next project. So I'll close this. And now we'll go to the door roller shaft. So this part was 100% a lathe part, so I kind of just went straight for the lathe part. I didn't even do milling center because it just wasn't worth it. So same thing with this one. The customer wants the turnkey part, so I modeled it up, and let me go ahead and do the simulation for the lathe. Torque turning center. I had to use a pretty sharp insert to get the tight angles, but faces the front, comes in here, cuts the slot. Looks very similar to that last part. Comes in here, does a little profile, profiles this portion, gets that little chamfer, and then it's going to come back here and get some relief to get the back chamfer. And then I believe it's going to come off with the part off tool. Yep, part off tool, boom, done. So that's the part. Not too crazy to program. So let's go to the bill of materials, the BOM for this one, to show the costs and all that, because that was also part of the project, was looking at the costs of everything and getting a little quote together for the customer. Alright. Yep, so here's the part. Here's the material requirements. I calculated the width of the bandsaw blade and the part length and parts per bar, rounded it down to assume a little bit of scrap, about 23 parts per bar. Looked at the parts per month, parts per year, parts for 3 years, and looked at the bars needed. And then I rounded up like 10 or so bars just to account for scrap. This is going to be the cost of the tooling for 3 years. It's about $200,000 in tooling. It's kind of crazy, but here's all the things we're going to need. One thing I would like to note is that, on lathes, the live tooling, it's not a true spindle. It's not like a real it's not like a real vertical milling center spindle. They're gear driven and they wear out. So about once a year you have to go and send those live tools to be rebuilt. So with the amount of live tools I used in over 3 years, that's like 9 rebuilds. So we're going to spend about $9,000 rebuilding the live tools. Just it's part of the maintenance for the machine. Each one of these parts is going to take around 2 minutes and 30 seconds. And let's see here. Yeah, this was the calculation for the capacity of the machine. So the machine, once again, I assumed a 60% uptime during a standard month, which I feel like is pretty conservative. I think some shops could push that to like 80% uptime, depending on how well they're dialed in. But you can see it's about 10,000 parts a month, and they need that many parts. So we only need one machine. That's basically what this calculation was for, is to see if we need one machine or multiple machines. Here's the standard operator rate calculated. So cost of one worker for one shift for a whole year, just pressing buttons and replacing inserts, is $41,600. Here's everything added up. Tooling cost per year should be there. I guess I just added up in a lump sum. Anyways, so here's all the costs. So we have labor costs per year, materials costs per year, flat rate machine setup, programming, and engineering time to get the job set up, and then I added like a standard shop rate for the lathe, so it pays for itself, so the shop makes money. So I did a first year, a reoccurring, to account for the things that already got paid for the first year, and then the total cost for 3 years. And this is basically just a demo of what a quote might look like for a customer. But that's this project, so we can go on to the last one, which wasn't too crazy. So we'll go ahead and open that up. We can close these out because I'm done with these. So the last project was an injection mold. Wait for that to load. There it is. Close this one out. Don't need to save that. So this is an injection mold. I found this little part on McMaster. It's a little handle, a little injection molded handle. I thought it would be a decent part to make a mold for. Full disclosure, this whole mold assembly, I got it from a YouTube video from somebody who does Fusion 360 tutorials. I'll pull it up here so you guys can see it. So this dude right here, he does Fusion 360 tutorials. So basically I took his, I didn't want to reinvent the wheel or, reinvent the mold. So I took his general core design, and then I edited these inserts. So these inserts right here, basically the way this is set up is that you have your injection molding assembly, and then these inserts you can just change out. So if you had a part with some different geometries, you could have these inserts sitting on the shelf so that you can have all of this tooling centered around multiple different parts. Now, the caveat with that is that if you have any parts with undercuts, or if you have any parts with like weird features where you need external, or you have parts with like through pins or something like that, something fancy, you wouldn't be able to share the same assembly for that part, because when molds start getting complicated, they start individualizing themselves and they can't be as universal. But in this case, I just have ejector pins straight through the part, so nothing crazy. So in theory, you could change around your some of your hardware here and some of your parts, but you wouldn't have to change out the whole entire mold to save costs for simple parts. Anyways, with that over, I'll kind of show you how I have it set up here. So I did design this gate system. Let's just go ahead and isolate this guy real quick, if I can. Isolate. There we go. Yeah, so the plastic comes in the top, comes through these gates, and it's kind of a bigger part, so I decided to add 2 gates or sprues to help fill the cavity a little faster. But yeah, now we can unisolate. So that's the top side of the mold, and then if we go and look at the bottom of the part, it's going to shrink down on 1, 2, 3, 4, 5 areas when the part cools. So I figured it would stick to this side of the part more. So I made that the side with the injector pins, is what I'm saying. Sorry for moving around so much, but it is a little hard to see. So here we go. Now, let's get a good view at that. Try to get a peek in there. Yeah, so basically, this is the part over here. That's the finished part that's going to come out, and then here's where it's sitting. So you can see I have 3 ejector pins kind of on the inside of 3 of the lobes. That way it's not pushing from one side to the other. It has like 3 points of contact to hopefully get it to push off evenly. So the idea is that it's going to shrink down on these 1, 2, 3, 5 little lobes, and then it'll get injected off right here. And then let me go ahead and hide some of these so we can see things a little better. Yeah, there we go. Yeah, so you can see we have this bore right here, it's going to go in all these cavities. And these guys are just going to go boop and push out. And let's zoom out back a little further so that we can see how the whole thing's going to work together. Show components. There we go. Alright. Hide that part. Alright, there we go. So basically, this is where the material is going to come in. Then it's going to go through here, through this little channel. And then let's see, where's that other part? I know there's more parts here. There we go. Okay. So the way this assembly is set up is that this is going to move. In reality, this side that's moving, it sounds a little backwards, but this is going to be the fixed side. And then this whole thing right here is actually going to move to the left. So this whole assembly right here, these parts are all going to move to the left. And there's a hole in this plate right here. It's going to, there's a hole right there in this plate. It's going to hit this bore. This bore is going to hit this plate. So when the parts, when this is all the way down, it makes a perfect part. Let's show that. So when this is all the way down, you can see those are perfectly lined up. And then as this plate, let's see, as this plate slides to the left, this is going to come in contact with this. It's going to hit this, and then all the ejector pins are going to push this part out. That's the plan. And I mean, honestly, if you're going to do this in real life, I think finding an existing tooling mold die on a GrabCAD or, you know, from a YouTube video is actually the best move, because that way you're not spending all the time doing something that somebody else has already done. But yeah, so that's this one. I can show a couple more details. Oh, also in the real world, you would want to put springs in here. You would want to do maybe some ancillary guide rods and then put some springs in there. That way it's always returning home to the same position. Also on this one, there's some out and in inlets for the fixed and moving side, so for cooling. In fact, why don't we do a little section view? Look at that. So you can see cooling channels. In fact, maybe we go here. Yeah, so that's pretty cool. You can see this is the insert, this is the mold insert, and then this is what this guy did for the cooling jacket. Then we go down a little further, and then you can see this one has some cooling jackets too. There's the cooling jackets. Obviously they're just drilled holes, but yeah. Anyways, so that's this one. That's the injection one. So I hope you guys enjoyed seeing all the projects. But yeah, that's it. All right, bye.